You already interact with the simplest AI agent ever built, and you don't even think about it. Your thermostat, your traffic light, the automatic doors at your grocery store. These are all AI agents, and here's the weird part. They're so dumb that they actually outperform smarter systems in high-stakes environments. Today, I'm breaking down every type of AI agent from the most basic to the most advanced, and exactly why each one exists, starting with the one you'll never look at the same way again. Simple reflex agents. This is the most elementary AI agent ever designed, and its entire existence can be summed up in 4 words: stimulus in, action out. No memory, no planning, no learning, nothing. A simple reflex agent reads the environment through its sensors, pattern matches against a set of hard-coded condition action rules, and fires off a response through its effectors. That's it, every single time. And the architecture is brutally simple. If temperature drops below 68 degrees, turn on the heat. If a car frame arrives at the welding station, fire the welding arm. If a vehicle is detected at the intersection, cycle the light. There is zero reasoning happening here, zero inference, just a lookup table connecting inputs to outputs at blistering speed. Here's where most people write these off. They hear no memory and assume simple reflex agents are obsolete relics from the early days of computing. But they're wrong. These agents are everywhere in 2026, and they're deployed in some of the most critical systems on the planet. Robotic welding arms in automotive factories run on this exact architecture, completing hundreds of identical welds per day with perfect consistency. Traffic lights across entire cities operate on fixed presence detection rules. Industrial safety shutoffs that kill power in milliseconds when sensors detect a fault. All simple reflex agents. But here's the fatal limitation. If a simple reflex agent hits the same obstacle twice, it tries the exact same failed move twice, and a third time, and a fourth, forever. No memory means no adjustment ever. It literally cannot learn from failure. And that limitation is exactly why engineers love it. Think about it. Zero inference means zero inference errors. Every possible input-output combination can be exhaustively tested and verified before deployment. You can mathematically prove that the agent will never do something unexpected. In safety-critical systems where unpredictable behavior could kill people, that's not a limitation. That's the entire point. In high-speed industrial contexts where a millisecond response beats sophisticated reasoning every time, simple reflex agents don't just survive, they dominate. The stupidity is the feature, but if you think an agent with no memory sounds limited, wait until you see what happens when you give one an internal model of the entire world. Deliberative agents. Reactive agents are fast, nobody's arguing that, but speed without understanding is just a coin flip that happens to work sometimes. Deliberative agents are where AI gets its first real brain. Here's the core difference. A reactive agent sees a red light and brakes. That's it. A deliberative agent builds an entire mental map of the world, reasons about what could happen next, and then decides what to do. It doesn't just respond to the moment, it thinks ahead. The loop works like this. Sensors feed information into an internal world model, which is basically the agent's understanding of reality. A reasoning engine takes that model and simulates multiple possible action sequences, predicting the consequences of each one. The agent picks the sequence it believes will produce the best outcome, executes it, observes what actually happens, and then updates the model based on whether reality matched the prediction. Then it does the whole thing again, and again, forever. Let me make this concrete. Think about a self-driving car. A reactive system sees a red light and stops. Done. But a deliberative autonomous vehicle is doing something wildly more complex. It's modeling the positions and speeds of every surrounding vehicle, mapping road geometry, tracking signal states, factoring in weather conditions, and then planning whether a longer but less congested route actually beats a shorter crowded one based on predicted total trip time. It's not just reacting to what's in front of it, it's simulating entire futures and picking the best one. One formal method these agents use is called hierarchical task networks. The idea is simple but powerful. You take a high-level goal like prepare a meal and decompose it into subtasks. Prepare the appetizer, the main course, the dessert. Then each of those breaks down further into things like gather ingredients, apply heat, plate the dish. The agent evaluates which decomposition path fits current conditions best, essentially choosing a strategy by working through layers of increasingly specific decisions. But here's the critical weakness, and it's a big one. Thinking takes time. All that reasoning, all that simulating consequences before acting, it introduces computational overhead that can be genuinely dangerous in situations demanding split-second responses. If a child runs into the road, you don't want your car running probability simulations for 400 milliseconds before hitting the brakes. And there's an even deeper problem. Every single prediction a deliberative agent makes is built on its internal world model. If that model's wrong, every conclusion it draws is wrong too. There are program garbage in, garbage out, but at a sophisticated planning level where the agent is confidently executing a beautifully reasoned plan based on completely flawed assumptions. So the trade-off is real. You gain intelligence, but you lose speed. You gain foresight, but you inherit a total dependency on model accuracy. It's the first genuine upgrade from simple reaction, but it comes with the vulnerabilities that reactive agents never had to worry about. But what happens when you take this planning ability and give the agent something even more powerful? An explicit goal it's trying to reach. Goal-oriented agents. This is where AI agents stop being clever and start being actually useful. Goal-oriented agents take everything deliberative systems do and add one critical upgrade. They operate in loops, not single passes. They analyze each step's outcome, compare it to what they expected, and when reality doesn't match the plan, they rewrite the plan every time, automatically. Here's why that matters. A deliberative agent books your flight, and if that flight is sold out, it hands you back an error. A goal-oriented agent, it doesn't declare failure, it revises. It explores alternative flights, adjusts dates, checks different departure times, and keeps iterating until it finds a workable path forward or confirms that no path exists. That distinction sounds small. It's not. It's the difference between a tool that breaks on first contact with the reality and one that actually solves your problem. The architecture behind this is surprisingly elegant. You've got three components working in a constant cycle. A planner generates an explicit task sequence, basically a to-do list, but one the system can rewrite at any moment. An executor follows that list step by step, and a monitor watches whether each step actually produced the expected result. When it didn't, the monitor flagged the planner rewrites the remaining steps, and the whole cycle starts again. This loop repeats until the goal is achieved or the agent confirms it's genuinely impossible. Not I tried once and failed impossible. Actually impossible. But here's where it gets really interesting. Delegation. The main orchestrator agent doesn't try to do everything itself. Instead, it assigns bounded subtasks to specialist subagents. One agent handles account lookups. Another interprets company policies. A third drafts customer communications. Each specialist operates in its own isolated context with limited scope, focused entirely on doing one thing well. Only the consolidated output flows back to the orchestrator. And this maps perfectly to how humans naturally organize complex work. You don't ask your accountant to write your marketing copy. Specialists outperform generalists on complex tasks, and goal-oriented agents formalize that principle into architecture. The React framework takes this even further by formalizing the loop into a thought-action-observation cycle. The agent reasons in natural language about what to do next, acts using whatever tools are available, observes the result, then reasons again. This isn't just efficient, it makes the entire decision process auditable. You can literally read the agent's reasoning at every step and verify it makes sense before it takes irreversible action. The last piece that ties everything together is persistent memory. An agent researching a topic across dozens of sources remembers which ones were reliable, which visualization formats worked in previous reports, and which approaches failed. Without this, the agent loses track by document 5 and starts duplicating work or contradicting itself. With it, you get coherent multi-session work that actually builds on itself over time. Goal-oriented agents are the architecture that made AI agents production ready. But finding a workable solution isn't the same as finding the best one. That's a completely different problem, and it's exactly what utility-based agents were built to solve. Utility-based agents. Here's where things get interesting and a little darker. Every agent type we've covered so far has the same basic problem. They find a way to reach the goal, and they call it a day. A goal-oriented agent that needs to get you from point A to point B treats every working route as equally acceptable. Left turn, right turn, highway, back roads. As long as you arrive, mission accomplished. A utility-based agent looks at that approach and says absolutely not. These agents don't just find a path to the goal. They find the best path. They do it using something called a utility function, a mathematical formula that scores every possible outcome based on how desirable it actually is. Not does this work, but how well does this work compared to every other option. Take an autonomous vehicle. A goal-oriented version just needs to get you to the restaurant. Any safe route counts as a win, but a utility-based version scores each route across multiple dimensions: safety, travel time, passenger comfort, fuel efficiency. Each factor gets weighted, and the agent picks whichever option produces the highest combined score. When two routes have nearly identical safety profiles, travel time breaks the tie. Every decision passes through this scoring system every single time. And this architecture shows up everywhere. Financial trading systems use it to calculate expected returns adjusted for risk and select the optimal trade. Healthcare allocation agents prioritize patients using survival probability, treatment benefit, benefit, and clinical urgency, all quantified into a single score. You define what good means mathematically, and the agent relentlessly pursues the best version of it. But here's where it gets complicated. Two hard limitations make this architecture far less clean than it sounds. First, computational explosion. An autonomous vehicle doesn't choose between three routes. It's dealing with thousands of possible steering angles, acceleration values, and timing decisions at every moment. Approximate algorithms help manage this, but they come with a cost. They can miss the global optimum. The agent picks a great option, but not necessarily the best one. Second, and this is the one that keeps researchers up at night, the utility function design problem. The agent will optimize perfectly for whatever you put in the function. Perfectly. If the function captures what humans actually value, you get incredible results. If it doesn't, you get an agent that confidently, efficiently, and relentlessly optimizes for the wrong thing. It will never question itself. It just maximizes the number. This works beautifully in domains with clear metrics: trading returns, travel time, fuel consumption. But the moment you enter territory involving ethical weight or anything humans struggle to quantify themselves, the whole framework cracks. You can build a system that scores a perfect 10 on its own rubric while completely missing what actually matters. That's the real story of utility-based agents. They're powerful, they're elegant, and they will do exactly what you tell them to, whether you told them the right thing or not. But if you think quantifying value is hard, wait until you see what happens when agents try to reason using pure knowledge and logic. Knowledge-based agents. Most AI agents learn by absorbing patterns. Knowledge-based agents do something fundamentally different. They separate what they know from how they think, and that distinction changes everything. Here's the core idea. A knowledge-based agent doesn't bury its expertise inside neural network weights or hard-code it into rigid rules. Instead, it maintains a centralized, inspectable knowledge base, a structured repository of facts, rules, and relationships that the reasoning engine queries whenever it needs to make a decision. The knowledge lives in one place and the brain lives in another. They talk to each other, but they're independent systems. That separation has real engineering consequences. When domain knowledge changes, you update the knowledge base. You don't retrain an entire neural network. You edit the repository. Different agents across an organization can share one knowledge base, ensuring everyone operates from the same source of truth. And because the reasoning process runs independently of what's stored, you can audit each piece separately. Verify the logic without questioning the data, or verify the data without questioning the logic. Now, how does the reasoning actually work? Two classical approaches dominate. Forward chaining starts from known facts and applies rules until it reaches a conclusion. Backward chaining works in reverse, starting from a desired conclusion and working backward to identify what facts would need to be true. One answers what follows from this, the other answers, can I prove this is true? Modern implementations combine both, supplemented by vector embedding search for conceptual matching beyond simple keyword overlap. Let me give you the clearest practical example. Contract analysis. A generic AI reviews a contract using patterns it absorbed during training. It catches obvious issues, sure, but it misses your organization's specific requirements. It doesn't know your internal policies or jurisdiction-specific regulations. A knowledge-based agent queries all of that. It pulls stored policies, regulations, and historical contract precedents from its knowledge base, then applies logical rules to evaluate the new contract against documented organizational reality. The output isn't generic, it's grounded in exactly how your organization operates. But here's where the real advantage kicks in. Explainability. When a knowledge-based agent declines a transaction, the entire reasoning chain is fully inspectable. Which facts were accessed, which rules were applied, how those rules produce the final decision. Financial institutions can show regulators exactly why a decision was made and defend it with a clear paper trail. Neural network agents literally cannot do this. The reasoning is locked inside millions of opaque parameters with zero transparency. But knowledge-based agents aren't perfect. Knowledge bases require a sustained expert effort to build and maintain. Domain experts have to identify what matters, structure it correctly, and continuously update it as reality changes. Neglect that maintenance, and the agent's decisions drift further from reality. And some knowledge resists structured representation entirely. Nuanced market dynamics, creative judgment, shifting preferences. You can't encode intuition into a fact table. So the knowledge-based agents are powerful, transparent, and auditable, but they demand ongoing human investment. The architecture works best when domain knowledge is stable, clearly defined, and expressible in explicit form. Law, medicine, regulatory compliance. That's where these agents thrive. But what happens when an agent needs more than facts and logic? What if it needs beliefs about an uncertain world, desires it can't fully satisfy, and the ability to commit to realistic plans when perfection isn't an option? That's exactly what the next next type was built for. BDI agents. Most agent types we've talked about were designed by computer scientists solving engineering problems. This one was designed by a philosopher trying to understand how humans think, and that difference changes everything. The BDI architecture comes from Michael Bratman's work on human practical reasoning. He wasn't building software. He was studying how people actually make decisions when they can't have everything they want. His framework breaks that process into 3 mental attitudes: beliefs, desires, and intentions. Here's the thing, each one does something completely different. Beliefs are what the agent thinks is true about reality, not what is true. What it thinks is true. Beliefs can be wrong, outdated, or incomplete, but they're the agent's working model of the world, and every decision flows from them. Desires are the outcomes the agent wants, and here's where it gets interesting, because desires can absolutely conflict with each other. You can desire a luxury vacation and desire to save money. Those two things are at war. A simple goal-based agent would either pick one or crash trying to satisfy both. But a BDI agent has a third component that handles exactly this problem: intentions. These are the filtered subset of desires the agent has actually committed to pursuing. Not everything you want, just the things you've decided to go after given your resources and constraints. The distinction between wanting something and committing to pursue it is the entire foundation of this architecture. The reasoning happens in 2 stages. First, deliberation, where the agent checks all its desires against current beliefs about what's possible and filters them down to realistic intentions. Second, means-ends reasoning, where it figures out the specific actions to get there. Let me make this concrete. A user tells a BDI travel agent they want to visit Cuba, stay under $1,200, travel in December for 8 days, and have a beach experience. Those are the desires. But December is peak season. Premium beach destinations on a modest budget during peak season? That's tension. A purely goal-based agent might just fail because it can't perfectly satisfy everything simultaneously. The BDI agent deliberates instead. It evaluates what's achievable given current beliefs about pricing and availability. The filtered intentions become quality beach experience in Cuba, 8-day duration, under budget. Means-ends reasoning then finds a package at $800 for 8 days in December. All 3 committed intentions satisfied. That's the key capability. Rather than failing when all objectives can't be simultaneously met, BDI agents deliberate to identify the best achievable subset, commit to it, and execute. And this mirrors how you and I naturally handle competing constraints every day. You don't abandon your entire vacation because the 5-star resort is over budget. You adjust. Now, implementation requires explicit data structures for each mental attitude. Beliefs get stored as a queryable fact database. Desires exist as goal specifications. Intentions are formal commitments. The deliberation logic connecting all 3 is structured and auditable, meaning you can trace exactly why the agent chose what it chose. That's more upfront engineering than throwing everything into a neural network, but you know exactly how the agent thinks because its reasoning is literally written out in logical steps. But here's the limitation nobody talks about. BDI agents are beautiful for structured reasoning about competing values, but they're slow compared to reactive systems, and they require someone to carefully define what counts as a belief, a desire, and an intention for every domain, which is exactly why some of the most effective modern systems don't pick just one architecture. They combine multiple approaches into something far more powerful: hybrid architectures. Here's the key insight that separates amateur AI design from engineering maturity. Picking one approach and committing to it is almost always wrong. Pure reactivity gives you speed, but zero intelligence. Pure deliberation gives you intelligence, but dangerous delays. Hybrid architectures solve this by refusing to choose. They layer both into the same system, running simultaneously, each handling what it's actually good at. The self-driving car is the definitive example, and it makes this click immediately. When the reactive layer detects an unexpected obstacle through sensor input, it triggers braking and a lane change right now. It doesn't wait for the deliberative layer to finish thinking. It doesn't ask permission, it just acts. That reactive response isn't strategically optimal. It might burn extra fuel, it might add 30 seconds to your trip, it might put you in a slower lane, but it avoids the collision. And avoiding the collision is the only thing that matters in that millisecond. Meanwhile, the deliberative layer is doing completely different work. It's optimizing the route to your destination. It's predicting how traffic patterns will evolve over the next 20 minutes. It's planning fuel-efficient acceleration sequences. None of that needs to happen in milliseconds, and trying to force it into millisecond timescales would make it worse, not better. This is what engineers call timescale separation, and it's what makes the entire architecture work. The reactive layer operates at milliseconds. The deliberative layer operates at seconds or minutes. These aren't competing with each other. They're specialized for completely completely different temporal horizons, like having a goalkeeper and a striker on the same team. Different jobs, different skills, same system. But here's where it gets complicated. Coordination between layers is where most implementations either succeed brilliantly or fail catastrophically. When the reactive layer deviates from the deliberative plan, say emergency braking for a pedestrian, it has to signal the deliberative layer about what just happened. The deliberative layer then updates its world model and revises the plan accordingly. This asynchronous communication is what enables both responsiveness and strategic coherence without one layer blocking the other, the failure mode you absolutely need to understand. If the deliberative layer's plans diverge too far from what the reactive layer can safely execute, the system starts oscillating. It follows the plan, then reacts to a hazard, then snaps back to the plan, then reacts again. The result is jerky, unpredictable behavior that looks broken because it basically is. And it gets worse. If the reactive layer doesn't communicate what actually happened back up to the deliberative layer, the deliberative layer's model of reality drifts further and further from what's actually going on. It's planning for a world that no longer exists. Getting this coordination right is genuinely difficult engineering. Nobody should pretend otherwise. But when it works across far more domains than just vehicles. Manufacturing robots combine reactive error recovery with deliberative task sequencing. When a part arrives misaligned, the reactive layer adjusts the grip immediately, while the deliberative layer resequences the remaining assembly steps. Smart home systems use reactive triggers for immediate user inputs, like turning on lights when you walk into a room, while deliberative components optimize energy usage across every device in the house over the course of an entire day. The satisfying thing about hybrid architectures is watching the pieces click together. Reactivity handles what deliberation can't do fast enough. Deliberation handles what reactivity isn't smart enough to figure out. Neither one is the right approach. Structuring them together for the right problems is the right approach. But if you think coordinating two layers inside a single agent is complex, wait until you see what happens when you have dozens of agents trying to coordinate with each other. Multi-agent systems. Everything we've covered so far has been about designing a single agent. One brain, one set of goals, one decision-making loop. This is different. This is about designing a society. Multi-agent systems aren't just multiple AI agents running at the same time. That's a collection. The defining feature of a true multi-agent system is that each agent explicitly models the goals and likely behaviors of the other agent around it, then uses that modeling to coordinate. Two delivery robots sharing real-time traffic knowledge produce route optimization superior to what either one would compute independently. That mutual awareness is the core mechanism. Without it, you just have a crowd. With it, you have an ecosystem. Here's where the architecture gets fascinating. Every agent in the system retains full autonomy over its own decisions. There's no single orchestrator calling the shots. Instead, agents communicate either directly through message protocols or indirectly by modifying a shared environment that other agents observe. Think of it like ant colonies. No ant knows the big picture, but individual ants leave pheromone trails that other ants detect and respond to. And from those local interactions, coherent colony-level behavior emerges. Route optimization, food sourcing, threat response. Nobody planned it. It just happened. Multi-agent systems operate on the same principle. Coherent system behavior emerging from local interactions without centralized planning. But training these systems is genuinely difficult. Multi-agent reinforcement learning has agents improving through trial and error interaction with each other, not just the environment. Every agent is simultaneously learning and adapting. And here's the problem. From any individual agent's perspective, the environment is constantly changing because the other agents are evolving their strategies at the same time. The ground is always shifting. Getting all of these agents to converge on stable, optimal behaviors when every agent is a moving target for every other agent is one of the hardest problems in modern AI. Now, the real deployments happening in 2026 show why this complexity is worth it. Transportation networks have autonomous vehicles coordinating trajectories and sharing route data across entire fleets. Manufacturing facilities run multi-agent systems where robotic arms, material handling units, and quality inspection agents dynamically adapt when equipment fails or demand spikes. One arm goes down and the entire system reorganizes in seconds without a human touching anything. Research applications deploy teams of specialized agents, one handling literature search, another running data analysis, a third doing synthesis, and they find connections across thousands of papers that isolated agents consistently miss. And this is a good time to clarify a distinction that trips a lot of people up. AI agents versus agentic AI. They sound the same? They're not. AI agents emphasizes individual agent design, how a single agent uses tools, manages memory, builds reasoning chains. Agentic AI emphasizes the system-level emergent behavior that comes from coordination between agents. In practice, modern deployments use both. Sophisticated individual agents operating inside multi-agent frameworks. The individual agent design matters. The coordination layer matters. You need both, but here's where it gets genuinely unsettling. The hard, unsolved problems at scale aren't theoretical. They're active engineering challenges in production systems right now. First, emergent behaviors. When hundreds of agents interact through local rules, system-level outcomes arise that no individual agent intended or predicted. Sometimes those emergent behaviors are useful. Sometimes they're catastrophic, and predicting which you'll get before deployment is, to put it bluntly, not something anyone has reliably solved. Second, alignment between agents. If different agents have even slightly misaligned objectives, they can work at cross purposes, each optimizing for its own goal while collectively making the system worse. Third, graceful degradation. When individual agents fail or coordination mechanisms break down, the entire system needs to handle that without cascading into total collapse. Getting that right at scale is an open problem, and that's the honest truth about where this field stands. Multi-agent systems represent the most powerful and most complex form of AI agent architecture that exists. They can achieve things no single agent ever could, but they also introduce failure modes that no single agent ever would. The frontier isn't about making individual agents smarter anymore. It's about making societies of agents that can coordinate, adapt, and recover when things go wrong. And we're still figuring that out. If you enjoyed this video and want to see more, click the video on the screen now.